Alright guys, welcome back. We're going to cover 2.2, and this is basically some more graphical ways in which we can display data. So, last class in 2.1 we mainly focused on the histogram, but we did also look at some other graphs as well, so we're going to extend that today. So, you can see the objectives are right here. We're going to look at how to graph and interpret quantitative data sets using stem and leaf plots and dot plots, and then how to graph and interpret qualitative data sets using pie charts and Pareto charts. Okay, so qualitative data is readily given to these two types. And then graph and interpret paired data sets using scatter plots and something called a time series chart. Alright, so we're going to start with stem and leaf plots. These are kind of neat, I think anyway. They give you a really good, just by making the stem and leaf plot, you get a real good sense of how the data is distributed or spread out. So you'll see here in a minute. So first of all, let's look at the data. Okay, so this is data concerning elephants. It says the data below represents the amount of water in gallons consumed by 24 elephants in one day. So as you can imagine, an elephant would consume a significant amount of water, and these quantities are quite substantial. One thing I noticed too, though, is that these are all like double digits. Okay. So, to make a stem and leaf diagram, you're going to, it says each data entry, whatever the number is separated into a stem, which is the entry's leftmost digit, or digits occasionally, and a leaf, which is the entry's rightmost digit. And then you should have as many leaves as there are entries in the original data set, and the leaves should be single digits. Okay. And then similar to a histogram, like I was talking about, it has the advantage that the graph still contains the original data. So see that a histogram, you lose the data. You're just seeing the frequency of the number of data entries in that particular class or interval, but you don't actually know what the actual data values are. So that's what's advantageous about the stem and leaf plot. Alright, so let's make one. I'm going to show you how to do this. Okay. Alright, so because these are double digits, then the leftmost digit will be part of the stem, and then the rightmost digit will be part of the leaf, essentially. Sometimes you can have, like if these were 3 digits, then you would let, probably in most cases, the left 2 digits comprise the stem, and then the rightmost digit comprise the leaf. Okay. What you're going to do, guys, is just kind of look at the leftmost digits in your data here. It looks like the smallest leftmost digit is a 3. Okay, so I'm going to start by writing a 3. And then that's followed by a 4, because we have several entries in the 40s. And then I'm going to go to a 5. You can actually start lower if you want. You could start with 2. There just won't be any leaves there, okay, because we don't have any entries that are in the 20s. And then I'll go to 6, to 7, and well, actually we don't have any in the 7s. But that's okay. So now what we're going to do, this is right. Yeah, you can draw a bar right here, and then you're going to start assigning the leaves to each part of the stem. Okay, so 38, typically you'll do this such that the leaves are in ascending order. So I need to look for my data value, my smallest data value that's in the 30s. So here I see a 32, and then I see a 33. So the 3 right here represents 30. So when I put the 2 right here, that represents 32. And then I will put another 3, and that represents 33. And actually, you don't have to keep commas between them. And then as you're doing these, go ahead and mark these out. And let's see, I see a 35 here. Oh, there's a 34 below that. So let's do the 34 and then the 35. So the 34 and then the 35. And then we've got a 38. And I believe finally we've got a 39. Okay. So the 3 is like in the tens place. So that means all of these numbers here refer to this 3. So 32, 33, 34, 35, etc. Now I'm going to go to the 4, and I'm going to find my lowest data entry that's in the 40s. So it's actually 40 itself right here. Okay. So the 4 is already there, so I'll put the 0 for the leaf. And then we've got 41, so I'll put a 1. And we've got another 41. And then, let's see, we just keep looking. I see a 43 next. I see a 44. A 45. A 46, and a 47, okay? So it's already looking like that's where the majority of our data is going to be concentrated. Now I'm going to go to the 5, and oh, I forgot, there were 2 45s. So let me erase the 6 and the 7, go ahead and add a 5 and then a 6 and a 7. All right, now for the 50s. I've got a 51. I've got 2. Well, I forgot a 48 too. Fortunately, the 8 can go at the very end. And then I've got 2 53s. You can see why this can be tedious. And I think that takes care of the 50s. Now go on to the 60s. So I've got a 60. So 60. I've got another 60, so I need another 0. And I forgot another 46, okay? So let me add another 6, and then a 7, and an 8. All right, so back to the 60s. Now I've got a 66, and then a 69. And that's it. Now we have accounted for every data entry thus far, okay? And so just by looking at this, guys, of course, there's really only kind of like 4 columns or 4 branches, you could even say. But you can see the majority of the data is right here. And in fact, most of the data is in the 40s. Okay, so anyway, like I said, this is a visual way in which you can see kind of how the data is spread out. All right, so that's a stem and leaf plot. One last thing before I forget it, you typically want to write a little key so as to know how to interpret this. So you'll typically do something like this. Just take one of the, so for example, I could do like a 3 and then pair it with this 2. And then just show that that's equal to 32. Okay, so that gives the viewer or the reader the key to actually understand what all of this means, or what all these entries actually mean. And then this 3 represents 33, and then 34, etc. Okay. So that's a stem and leaf plot. Now let's take a look at a dot plot. So there's not a whole lot of examples in the notes. I mean, there are examples, but not very many that I work out. Okay, so a dot plot is really similar to the stem and leaf plot. Okay, the only difference is you're going to have horizontal axis. It's calibrated. And for each data entry, you're actually going to put a point or a dot right over that particular number. And if there's more than one, you're going to have more than one dot vertically arranged here. Okay. And again, this is another great way to see and observe how the data is distributed, and also to observe any what are called outliers. Okay, so this one right over here, the dot right here that represents the data entry of probably 149, that would be an outlier. So let's look at this this data set. It is the number of text messages sent. Okay, so we're ranging anywhere, it looks like, from down here 16, so evidently there's a data entry in here that's probably around 16, all the way up to here, this highest entry, which is 149. So the range of number of text messages sent, and I'm assuming this is over the last week. Okay, these are cell phone users on one floor of a college dormitory. These numbers actually seem quite low to me. Maybe if this was, when texting was in its infancy, I might be more prone to believe this. But in any case, we've got all the data plotted here. Okay, so if you're doing a dot plot, 58, for example, you just figure out where 58 would be and you put a point right there. Okay, and then, for example, right here at this seems to be maybe 28 or 29, where you have values repeated. Let's see, yeah, 29. See, there's two 29s right here. There's another 29. You just put, if you have four values of 29, you just stack them one right on top of the other. All right, now I want to zoom in for a minute. But by doing this, guys, this shows you the actual distribution of the data. So you can see that it's really pretty rare to have someone texting anything beyond 85 or 90 messages per week. Most of the data lies below that, and I would even argue the majority of the data is right here. And it's interesting, too, because we sort of see two groups of data, right in here, and then over here, there's like another little bell curve, okay? So it's interesting because when you look at a graphical representation of data, you can see trends, and you can make inferences about what's happening. So, this little curve right here, this might correspond to a specific group of students that maybe has more free time, and then this group over here, this little curve could correspond to a group of students that has less free time and is not as concerned about texting. Okay, so we could start making some inferences or some hypotheses to try to explain what we're seeing here in the data. But anyway, I think that's pretty neat. All right, so these are both two ways in which you can display quantitative data, okay, so numerical data for the most part. All right, so let's look at some ways that we can display qualitative data. We can use a pie chart, and I'm pretty sure everybody in this class has seen a pie chart before, okay? So typically it's a circle divided into sectors, and the size of the sector is proportionate to the percentage of whatever it is that you're talking about. Okay, so in this case it's sales by department. So at this particular grocery superstore, you can see here that electronics comprises, it looks like 18% of all the sales. Okay, and then you can see over here, that looks like, to me, shoes. The sale of shoes comprises just 2% of the businesses that this particular grocery superstore does. So this could be like a Walmart superstore or something. Okay, and this is always the case, guys. The size of each pie or a piece of pie is always proportional to the percentage that particular category occupies. Okay. All right. And then another is called a Pareto chart. I think of this as a bar graph, a bar chart. Now remember I said a histogram was sort of like that, but a histogram, guys, is typically for quantitative data. And if you remember, furthermore, those bars are touching with a histogram. That's not the case with a bar graph or Pareto chart. Okay, so the heights of the bar, they represent the frequency or could represent the relative frequency, so they're similar to a histogram in that way. But the bars themselves represent qualitative categories, as you can see here. So the data here is the top 5 causes of death in the U.S. And so the height of the bar will tell you what's the leading cause of death in the U.S. And you can see here it's heart disease. It just barely edges out cancer. But these are looks like the 2 biggest leading causes of death in the U.S. And they actually have this vertical axis calibrated to be the actual number of deaths in thousands. So you can see here with heart disease, it's close to 630. That would be close to 630,000. Okay. Also, guys, one other thing. Let's see. Yes, right here. With a Pareto chart, the bars are positioned in order of decreasing height, okay, with the tallest bar positioned on the left-hand side. So that's typically always done with these. All right. This section is not real long, and I looked at the homework just a minute ago. The homework, guys, is just looking at these different types of graphs and interpreting them. So I don't think the homework's going to be too challenging for you. And then the last 2 that we're going to talk about is a scatter plot and also a time series chart. Okay, these are typically used when we have paired data sets. Okay, so when one entry of the data set corresponds to one entry in a second data set, the sets are called paired data sets. So you can sort of think about in your algebra classes those ordered pairs, right? That we obtain from functions. So for any particular value of x, there corresponds, one value of y, okay? That's really what a scatter plot is. Just a collection of ordered pairs. And then you just plot them on a 2-dimensional coordinate system like this. And you call it a scatter plot, okay? And by looking at a scatter plot, guys, you can again determine trends in the 2 variables that you're measuring. So let's look at this one. This is a famous data set of petal length in milliliters and petal width in millimeters as well. So we're measuring both the length and the width of the petal. And so you can see that along this horizontal axis, we are measuring the petal length, and on the vertical axis, the petal width. And so you have all these ordered pairs, okay, from all those measurements, and you plot them in here. And then you look at this, and you try to make, you try to figure out if there's a correlation between petal length and petal width, okay, because you're trying to let the data tell a story. Now, if this, whoops, I didn't mean to do that. If this data was just scattered all over the place and there was no apparent trend, then you would say probably there's no correlation between the 2 variables. Like a petal's length has no effect, or there's no association there between a petal's length and a petal's width, okay, for these 3 different species of iris. And this was done back in 1936. But as I'm looking at this, I'm seeing a trend here. A lot of these data points sort of form a straight line. And also, guys, I'm noticing that maybe I've got a little partial line here I've got another partial line that kind of corresponds to this data set, and I'm seeing a third grouping of data right here. Because remember, this said we're talking about 3 different species of iris. And so by looking at this, these lines are going uphill. And all these data points seem to cluster around these lines. So that tells me that as the petal length increases, because these lines are going uphill, or the data seems to be going uphill, that as the petal length increases, the width is increasing as well. And that's why you're seeing this upward trend, okay, in the data for all 3 species here. And guys, I would be willing to bet that's probably universal for the most part. Not just with irises, but all sorts of flora. All right, so there's you an example of a scatter plot. Last thing we're going to look at is a time series chart. Okay, so you only typically use it, although you could use a time, you could do a scatter plot, but really a time series chart is just a scatter plot in which the horizontal axis represents time. So see here, okay. So you're still plotting these ordered pairs. You still have 2 axes and 2 variables of interest, but the horizontal axis is always going to represent time for a time series chart. So it's quantitative data in which it's taken at regular intervals of time. Okay, so like I said, similar to a scatter plot, the x-axis is time, and then the data points are connected with a line. And so we've got an example right here. So we've got some data. It says the table lists the number of motor vehicle thefts in millions and burglaries in millions for the years 2005 through 2015. Construct a time series chart for the number of motor vehicle thefts. Okay, so if you were just looking at the motor vehicle thefts as a function of time, these would sort of be like your ordered pairs. You could sort of think about the specific years as like your x's and the number of thefts in millions as your y coordinates. Okay, and so if you were to plot those, for each year there's a certain number in millions of motor vehicle thefts. Okay, so in 2005 we've got 1.24 million thefts, so you put that point right above the 1.2. And then you do that for the rest of these pairs. Hey. Alright guys, sorry about that. One of my colleagues had come by the office. So anyway, just to kind of finish up here, so you would plot these different ordered pairs, and then you would just kind of connect them with a line and kind of see what the trend is. And so you can see here that over that decade from 2005 to 2015, it looks like we see a pretty drastic decrease in thefts from the years 2006 to about 2009, and then it starts to kind of level out. So but you can see there is a pretty drastic decrease in thefts over that decade. So anyway, like I said, this is a shorter section. A lot of your homework is just going to be, you will have to make your own stem and leaf plot, but most of it's going to be looking at these graphs and interpreting them. Okay, so anyway, let me know if you have any questions, and I'll see you in 2.3.